Okay, lab partner, we went out with a bang. This is sweet data. I did a couple of the calculations just to make sure that it's all in what it should be, and it is. And I'll tell you, it is sweet. All right, now, let me go through what we need to do. Now, what you need to do. So at this point, we have done the data, okay, for each of the 9 trials, starting height. Okay, so we did the heights. We know the heights. Let's put those on the board. We have the heights, so put those up there on the board for you. Now, the small hill, what we're doing is potential and kinetic energy. And we're going to use those equations. And when you use equations in physics, remember you have to have MKS, meters, kilograms, seconds. So we need meters. Now, the height of the small hill was 0.9 centimeters. You can't use that in the equation. You have to make that meters. So make that meters. So move it over 2 places. Oh, that is not a good marker. It's a Dyer marker. It's a Dyer. Yep, sorry there, buddy. So move it over twice. The decimal point 2 places to the left. 0.009 meters is the height of the small hill. Do the same thing for the heights of the medium hill and the height of the high hill. Take those centimeters, which we already went over, showed you that data, those measurements. You'll have to trust me on those. Okay, and move over the decimal point 2 places to the left on both of those, because you do have to use meters. Okay, so what are we doing? Well, what you're going to do for calculations, for the potential energy of the air cart relative to the photo gate. So what I wanted you to do for calculation number 1 is just figure out the potential energy of that air cart relative to the photo gate. What does that mean, relative to the photo gate? That means from the height that the cart was above the height of when it goes through the photo gate, or in other words, the height of our hill. So for the small hill, calculation 1 for the small hill, now you're going to have to do a calculation for each one of the trials. We have 9 trials, all right? I hope you wrote that data down, okay? I hope you did. I'm not going to write it all up here on the board because you have it. You watched the video and you wrote it down. So what we're going to do is you're going to have 9 calculations for each calculation. So for calculation 1, you have to do this 9 times. And it does become repetitive, so I would strongly suggest that you make a calculations table. You could do that, make some kind of a calculation table, and you figure it out. You're a relatively smart lab partner, yes you are. So you just give me maybe a calculation table. It could actually look like this if you want. You make 9 spots, and then for the height of the potential energy, you can put the potential energies in each spot. However you want to do that, but organize. But here's what I would do. So my very first trial, this trial right here, I'll do this one for you. Okay, this trial, the potential energy. So for trial 1, the PE equals mgh. So the PE equals, and you don't have to show these calculations, what I'm doing for each trial. It gets really repetitive. The mgh, okay, so we need the K, and equals the velocity, yep. So m, that was 200-gram cart. What should I put it in? Kilograms. 0.2 kilograms multiplied by 9.8. The height of the hill in meters is 0.009. So 0.009. So multiply that out, and you'll get an answer for the potential energy for trial 1 of that air cart, and 0.2 times 9.8 enter times 0.009. All right, and we would get 0.0176. 0.0176. Can you still see this, lab partner? 0.0176. What would the units be? It's energy. Joules. And that would be the answer. You're going to get that. Okay, you should. We all have the same data. So you're going to get that. And that's going to be the answer for the first out of the 9 calculations for the first calculation. That's just your trial 1 calculation. Then you go ahead and do calculation for trial 2, for trial 3, for trial 4, 5, 6, 7, 8, and 9. So 9 times you're going to do that. But you don't have to write this out 9 times. I just wouldn't do that. Just go ahead. If you just show me, how to do one trial, then I know that you know how to do it. And then you can just go ahead and like for trial 2, like we did this one as trial 2. It doesn't make any difference which one you call trial 2. But do this though. Make these trials 1, 2, and 3. Make these 4, 5, and 6. Make these 7, 8, and 9. All right? That'll kind of keep things organized. So for trial 2, you'll take the height of the hill is still 0.009 times 9.8, but you're going to multiply it by 0.3 because that was a 300-gram cart for the second trial. You just go ahead and do that, and then just give me the answers. So you can just calculate these out. You don't have to keep writing them out. Do the calculation on the calculator and get an answer. So for the second one, I'll do this one with you too, lab partner. So the second one, what are we going to do? We're going to take 0.3, okay, 0.3, going to multiply it by 9.8, and then multiply it by 0.009, and you get 0.0265. So for trial 2, 0.0265 joules. And that's all you have to do. And you can just keep going and do each one of the trials and just show the answer after you've shown how to do it once. It's the same, okay, each time. And just be careful when you go to the medium hill for trial 4 that you are using the height of the medium hill, not 0.009 anymore. And the height of the high hill down here for trial 6, 7, and 8, or 7, 8, 9, not the height of the medium hill. So just be careful of that and keep changing those masses. All right, that's calculation 1, just figuring out the potential energy. 9, there are 9 calculations for each one of these, so calculation 1 has 9. Okay, now 2. It says the theoretical true velocity of the cart as it passes through the photo gate. The true velocity of the cart as it passes through the photo gate. Think about the Grinch problem. With the Grinch problem, I can get rid of this now. With the Grinch problem, we had the Grinch at the top of Mount Crumpet, and we calculated the Grinch's PE. Then we said, well, with no friction, it all becomes KE at the bottom. And what did we do? We took the potential energy at the top, and we figured out the velocity at the bottom. That's what we're doing here for calculation 2. So for calculation 2, you take the potential energy at the top of the hill, okay, which we have now calculated, so, right, because you did that from calculation 1. And I forget what, I'll do the first one for you. I'll do trial 1. Okay, and now, so what happens? The PE at the top, which was equal to 0.0176, I think. Oh, I lost it. No, I'll go back and do it again. 0.009 times 9.8 times 0.2, 0.0176. So the potential energy at the top should become the kinetic energy at the bottom. So now, how do I figure out the velocity? That equals that. These are the same, assuming no friction loss. Okay, and we almost are virtually frictionless. Almost. We haven't lost all the friction, we've lost a lot of it, so we're assuming no friction. Okay, so that becomes that. And this, for trial 1, is 0.0176. So let's write out the kinetic energy equation. Kinetic energy is 1/2 mv squared. So KE is the PE. 0.0176 equals 1/2 mass of the cart was 0.200. So for the first 3 trials, 0.200. And then I'm going to solve for the velocity. And let's see what we should get. All right, we'll do the math on this. So I'm going to multiply this by 2, divide by 0.2, take the square root. So 2 times 0.0176 divided by 0.2 equals V if I take the square root of it. So that's V squared, I want V. All right, what do we get? Okay, times 2, enter, divided by 0.2, enter, second function, square root, second function, answer, boom, 0.42. The math says we should be getting 0.42 meters per second. So for trial 1, calculation 2, we should be getting 0.42 meters per second. Try that on your own, see what you get. All right, okay, all right. Now, you're going to do the same thing for trials 2, 3, 4, 5, 6, 7, 8, 9. You're going to calculate what the math is saying the velocity should be based upon potential energy at the top of the hill. Since it becomes kinetic energy, we can then go ahead and use that to solve for V. So for each one of these, what you're doing is to solve for velocity. Okay, as you're multiplying 2 times potential energy divided by the mass of the car. And that gives you your answer. Now I want to point something out. Okay, we have the velocity as it should have been 0.2, and it comes out to be 0.68. Right? That's what the theoretical, this is our theoretical. This is what should be, this is called the true value. These are the experimental values. All right, so you write those down, right? You got those all written down. I do, but I'm not going to show you, lab partner, because you have to watch the video. If you didn't, if you just fast forward this video, go, I'm not going to watch it, let's get the data. Our velocities, and I have done a few of these, and I'll do one more. I'm not going to tell you which one I'm going to do, but I'll do one more for you here. Figuring out what the velocity should be. Okay, I'm going to take 2. Okay, let's see. So 2 times. Okay, all right. 0.51. So what I ended up getting is a number, again, on one of the trials, 0.851. Well, less. So the values theoretically are always coming out, and I did a number of these, so I know this is true, consistently lower than the experimental values. So they're coming out just a little bit lower. Okay, well, I wonder why that is. Did you notice something, lab partner? I hope you did. I hope you look at that lab data and you noticed that for the same hill, there was virtually no difference between the velocities when we changed the mass. Why is that? Why is that? I'm not going to tell you the answer. I hope you've got it figured out at this point. I mean, I might even go back to calculation 1, and looking at calculation 2, I hope you've watched the videos that when it comes to PE versus KE, what about the mass? All right, we changed the masses and we got no difference in trial 1 or trial 2 and trial 3. We had none at all. They're identical. And the rest of them were all really close. The biggest differences we had in any of that data was trial 4 and trial 6. 0.695, 0.703. That was a difference of 0.008 meters per second. That is 8/1000ths of a difference in meters per second. That was the biggest difference. So we're different. We're going a difference in 1,000th place. That's basically irrelevant. So essentially, there's no difference in the velocities as we go across. They're all, statistically speaking, the same. Why is that? Okay, good question. All right, so what do we have to do then for calculation 3? Do a percent error for each of the velocities. You're going to use, so 9% errors, 9. You're going to use this calculated value as your true value. You're going to use the experimental value that we got doing the lab on the vernier device that we wrote down there as your experimental values. Do a percent error for each trial. Remember, true minus experimental divided by true, absolute value, multiplied by 100, see what we get. Typically, we are going to be off by a little bit. I'll run through the first one for you, just so let's just see how far off we are. So there's my true value for trial 1, so 0.42 minus 0.468, enter, divided by 0.42, enter, and we're off by 11%. I was going to say typically 10%, sometimes 10 to 15%. Why is that? Why are we off by a little bit every single time? I know we always are. It's always off by a little bit, usually. Like I said, 10 to 15%. Why is that? I don't know, partner. You come up with the reason. You think about it for a second, right? We're assuming virtually frictionless, and did you notice another pattern that the more mass that we added, the slightly, it's again, relatively insignificant. We're looking at like 1/7,000 of a meter per second, but slightly faster, just very, very slightly faster. I wonder why that is. Does it all make sense? I hope it does. I'm not going to give you the answers, partner. No. You got to think about it. Come on, you should be thinking about this stuff. You're good. All right, and what else do we have to do? So now we've got our data table done. You've done your 9, 9, 9. I'm speaking German. 9, 9, 9. 27 calculations. Oh, what else? Are we done? No, not quite. Down here at the bottom where it says discussion, these are your questions you have to answer. So answer these 2 questions right here. Answer those 2 questions. And it says, do your results indicate a relationship between PE and KE? If so, what is that relationship or the connection between them? Just answer that question. What's the connection between them? Number 2, is the PE converted to KE in moving objects? Why or why not? So this is all. Is all of the potential energy at the top of the hill converted to kinetic energy? Is every little drop of it converted? This is real world. This is IRL in the classroom, right? Not math on the board. Well, not that math isn't real, it is, but what happens in the lab that we assume doesn't happen on the math. Okay, so there in real life might be a reason why. Okay, that's all I got to say. I'm not going to say anything else about that. Okay, you do it. All right, and that would actually wrap up our last lab together. Do those 2 questions, do 27 calculations, and give me that data table. And like I said, you're a great lab partner, and I hope to see you again very soon. Okay, lab partner? All right, I'm crying. I get off before I cry. I'm crying, lab partner.